It's my pleasure to introduce Dr. Martin Berzins, who co-authored along with two of his former students, John Holmans and Damodar Sahasrabuddy, the paper entitled Porting Uintah to Heterogeneous Systems. My PASC22 paper's co-chair, Kate Evans, will present the Best Paper Award to Dr. Berzins later today in the closing session and award ceremony this evening to recognize this paper as representative of the spirit of PASC22 and of interest to a broad audience at the conference. Dr. Berzins is in the Scientific Computing and Imaging Institute at the University of Utah, where he's a professor of computer science. He's also a visiting professor at the University of Leeds in the UK, where he was previously a professor of scientific computing and research dean for engineering. He earned his PhD in computer science at Leeds in 1981 and has worked in the fields of mathematical software, numerical analysis, parallel computing, and more recently, problem-solving environments and grid computing. Much of Professor Martin's work has centered around tackling challenging problems in computational fluid dynamics, combustion, atmospheric modeling, and lubrication modeling. Dr. Berzins.
Thank you. Okay, so this work came about through our participation in the US Department of Energy Exascale effort with the Argonne National Laboratory, and we've been working for quite some time with the machine, well, the effort that will become the Aurora machine shortly. And what we were doing is trying to think about how to put together a benchmark that would be a good exascale benchmark, and then to show how this benchmark would perform on different machines. And so what we did towards the end of last year and through this year was to do some experiments on different machines to try and understand the performance of the benchmark that we're putting together. Now, John Holman and Damodar Sahasrabuddy are the two students who worked on this and who did a lot of the work. And my role was to kind of, put together the strategy and move us in the right direction in terms of thinking about what the benchmark would be and to try and figure out how we could show how well it worked. And what I'm going to do is tell you about that effort. And the emphasis really is on sort of whether we can get to performance portability for the kind of programming approach that we use. Now, that approach is a bit difficult because we are working with asynchronous task-based systems, so it's not the same as a standard programming model, but that has many advantages too. So what I'm going to do is talk about a little bit about exascale machines. I'm going to talk about the Uintah approach, which is an asynchronous runtime system, an AMT, a many-tasking system, and talk a little bit about how we get portability across CPUs and GPUs. I'm going to talk about some of the things that we had to do with the code to improve performance, and then I'm going to show you some benchmark results running on a high-end CPU machine, the Frontera machine that's run by NSF, and compare its performance against the Summit architecture, and we'll see some interesting things about how these two architectures compare. So I want to thank the Intel One API Center for funding us during this work. We also had some funding from NSF. I want to thank Argonne and Oak Ridge for giving us time on their machines. And this effort is based on the work of many, many people over the last, sort of easily 25 years with the Uintah software on asynchronous approaches. So let's talk a little bit about exascale. I mean, exascale, we now have an exascale machine. But the run-up to that was the Summit machine at 200 petaflops, the Fugaku machine, which has been on some of the posters here, at 415 petaflops, a sort of very novel CPU-based, ARM-based CPU design with vectorization. There are two Chinese machines about which I don't know very much, except there have been reports in the computing sort of open literature about sort of exascale performance, the Ocean Light and the Chang'e 3 machine. And now we have Frontier, and we have two other machines coming in short order, the Aurora machine, which is Intel GPU-based, and El Capitan, which again will be an AMD machine like the Frontier machine. At the same time, all these architectures are different, and we also need to be able to run on CPU machines, such as the NSF Frontera machine at the Texas Advanced Computing Center, TAC. And so what we need to do is to have a sort of common programming approach that works across all these different architectures. And in some sense, we're back to where we were before MPI kind of standardized how we write parallel codes. And if we look at these machines, it's a little bit challenging to get performance out of these machines. So what I've done in this table is I've listed the different architectures going back to the DOE Titan machine at Oak Ridge, the Summit machine, and then the AMD graphics processors, the Instinct, the ARM processor that's in the Fugaku machine, and the Intel processors in the Frontera architecture. And what I've done here is I've listed the double precision peak performance, which is basically sort of ranging from 1.3 teraflops to 3 teraflops or 48 teraflops on some of the architectures, and looked at the memory bus speeds. In other words, how fast can we feed the processing units? And if you look at the ratio of those two things, it's kind of challenging, because what you see is that in order to make full use of these architectures, you really have to have a high arithmetic intensity. And so that means that essentially you need to be able to be reusing every piece of data that you move into for execution and to get full performance. And if you look at the transfer rates from CPU to GPU, it's even more problematic because those rates are even slower in some ways. So the real difficulty is, can we even achieve this kind of performance, or how will this memory bus and peak floating point performance impact what we actually see with the different applications that we run? Here's my analogy for using GPUs, okay? So it's a bit like going shopping, doing your weekly shop in a sports car. It looks great, it goes fast, you can't really get a lot of stuff in the back. And the real question is it worth it? You know, I mean, you'll be moving along in low gear or whatever, because for sure it'll be, well, some kind of crazy transmission. And you don't really, it's hard to say, well, is it really worth using this for your application? So what we're going to see is whether or not it is. And the answer kind of came as a surprise to me in some ways as well. And I'll show you at the end of the talk whether or not it is. If you look at many of the computational models that we have, they're characterized by the fact that for every data item, you really only have, if you're lucky, as somebody said to me yesterday from the weather forecasting community, one floating point operation per word, okay? So if you think back to where we were with our table a couple of slides ago, we need a lot of floating point operations per word, but many of our codes just don't have this, standard fluid dynamics codes and so on. And if you think about areas like weather forecasting, it's even more complicated because you have data assimilation and all kinds of things going on. So it's not clear that you can necessarily get sort of peak performance. Now you can tune some of those codes, you can have special methods and everything else, but if you're sat in the middle of, you know, a couple of million lines of complex C++ like we are, sure, if somebody says, tune your code, I just say, okay, give me a few $1 million and let's tune it. Because it's very difficult to tune a large code, and only organizations like the National Weather Forecasting and so can afford to go into this sort of space. The graph shows you, the graph on the right shows you sort of some results from multigrid, and essentially what you're seeing is that it's a bit difficult to read, but the green is high bandwidth memory, and it's showing the different levels from multigrid, and what it's showing essentially is that the performance tracks high bandwidth memory, which is that sort of transmission rate that I showed you for GPUs. So what's the application that we're working with? Well, it's kind of ironic at a conference that hopes to sort of, move towards using computing for the good of, mankind and how we advance, because our application is somewhat controversial and old-fashioned. But here is a really scary statistic for you. Somebody said, well, 20 years ago, what proportion of the world's energy was produced by fossil fuels? And the answer was 80%. Anybody care to guess what the answer is today? 80%. So we haven't really moved at all. We're consuming a lot more energy. So there's a need to try and make sure that if we do use these techniques that we don't like to have, like coal, for example, that it's done in a much more efficient way as much as is possible, because some countries are not moving away from that as quickly as we would like. So anyway, so we worked for a while on sort of combustion modeling, and what we're doing is sort of turbulent combustion, as you can see, in a clean coal boiler, which is 60 meters tall, about 10 by 20 meters across at the base. And so this is a natural exascale problem, 10 to the 14 variables. We're using high-order finite volume methods, the standard conservation laws, turbulence models. Also, there are many different features to do with this. In particular, you can see the turbulent flow, but also the main form of sort of heat transmission is through radiation. So we have to model radiation. And radiation is nasty for modeling, because what we have to do is to think about how radiation goes everywhere. And so it connects everything to everything. So it's a global kind of operation in the middle of this huge computational space. So it's not at all clear you can even make that scale. And one of the things that we did is show that you can. So, okay. So this is the problem I'm going to talk about. I'm not going to talk about the whole code, but maybe just sort of talk about two of the key features of it, which are radiation and flow. Let's talk a bit about radiation. So radiation modeling, it has this global feature, which is potentially problematic. And the way that we get around this is through the use of adaptive meshes. And what we do is we essentially have a fine mesh around the radiation source, which is actually every patch there's radiation emitted, and that mesh for that patch, the mesh gets coarser the further you move away. So we have a sort of coarser mesh and in the far field, and a fine mesh close to the source. And what that means is we can essentially limit the amount of communication that we do, which is the key feature in making this scalable. And even though the sort of computational mesh that we use is very dense for the turbulence, the radiation mesh involves adaptive mesh refinement in that way, and that allows it to scale. And on the bottom of this, you can see some scaling results that we originally got from the Titan machine, and you can see that in going from 16K CPUs and 1K GPU to 256K CPUs and 16K GPUs, we get actually really very good scaling. Every sort of step in there is a reduction by a factor of 2. And so we were able to make this scale, and so in fact the algorithm itself is inherently scalable because it uses this adaptive meshing for the treatment of radiation. And we were able to see this scale on the other machines that we moved to, the other GPU machines like Lassen and Summit, without any further tuning of the algorithm at all. The asynchronous approach that we use goes back an awfully long way. It starts off in the 1960s with some work. Probably one of the best pieces of work on this was a PhD thesis by Vivek Sarkar in the late 1980s, and in which he laid out all the main ideas, but at a naturally very small scale because large scale wasn't available. And then sort of extensions of this, the Charm++ work, at Illinois is one, and Steve Parker at the University of Utah used a similar approach, which became the beginnings of the Uintah software, which I'm talking about today. A lot of these approaches were sort of based originally on static execution of these task graphs, but of course what we do now is fully dynamic execution. And the idea is shown with these 3 blocks of mesh patches, and each of them in the Uintah code has its own task graph. But we don't have a global task graph or try and optimize a global task graph because that's too difficult to deal with when you're trying to move towards very large scale and exascale and so on. So what we have are these individual task graphs, and in the case of the example I'm showing, it's a simple halo calculation. So the blue cubes are the sort of core of each patch, and the green slabs are the halos or ghost cells that are used to pass information between the blue cores, essentially. And so we have communication between the different task graphs. but they're actually independent entities, and that makes it possible for us to scale this up to the full range of all the architectures that we've run on. And there's a degree of automation in this, in the sense that the user just specifies the patches and the meshes and the halo levels, and then everything else is automated inside, including the generation of the communications, the MPI communications between different MPI tasks. And the idea behind the asynchronous execution is that we do useful work while we're instead of waiting. So what we do is we keep each MPI process busy with the internal patches and prioritize sort of communication and prioritize making communication possible. And that's a very scalable and very sort of useful strategy for making the best use of these architectures. And so we avoid waiting and make it possible to scale. The Uintah code itself is kind of complicated. It sort of has there's a lot going on. We essentially have applications layers. We have 3 applications layers. Arches is a combustion code, NPM ICE is a particle code, and NPM is a particle code, ICE is a fluids code, and NPM ICE is a mixture of fluids and particles. Wasatch is a kind of problem-solving environment that sort of drives a whole bunch of different discretizations. We have a performance portability layer that I'm going to talk about, which is essentially how we write each different, how we write our loops, and so that they can be mapped onto CPUs and GPUs. We make use of the outstanding hypersolver that's been developed at Lawrence Livermore by Ulrika Meyer and Rob Falgo and various other people. And we use Visit for visualization and an I/O library called PIDX from Valerio Pascucci and his group at Utah. And underneath all of this is a sort of this task graph approach that I talked about, but it's sort of the implementation of that uses a runtime system which has a sort of a task scheduler. We do load balancing. We have a data warehouse. We have multiple data warehouses on both CPUs and GPUs and MPI communications. So adaptive execution, automatic generation of the task graphs, and asynchronous sort of out-of-order execution, which involves work stealing and overlapping of communications and computations. And we use CoCos for the performance portability layer, and we've been working with those guys since about 2015. As soon as that was available, we jumped in and started using it. So here's a sort of diagram of the runtime system, and you can see the different data warehouses here on the CPUs, on the GPUs. We have execution of tasks on the CPUs and the GPUs. We have a task queues for the CPUs and the GPUs. We have a task graph here, and we run tasks on CPUs and GPUs. We pick up tasks as soon as they're ready to execute and execute them. And many other people are doing this, but we've been doing this for an awfully long time and have been very, very successful with it. And the sort of the input task graph is the one thing that the user has to do in terms of specifying how the tasks are connected in some way, and there's no way of getting around that really in terms of programming in this way. So programming is a little bit more conceptually challenging, but it also has a lot more freedom to it. CPU to GPU data transfer is problematic because, as I mentioned earlier, that's one of the weak points of all the architectures. That transfer is problematic and slow in general, although it's getting better all the time, and so on. So I don't expect you to make sense of this very complex diagram that we have here, but wait, hang on, you can't see my pointer, can you? I can see it on here, but not on here. I thought it was being transferred. Never mind. Okay, so we have asynchronous things like host-to-device transfer. We have our GPU data warehouse, CPU data warehouse. We have a synchronous device-to-host transfer for completed tasks. This is the logic that sits underneath the execution of tasks on CPUs and GPUs, and it really is quite complicated structure that we developed over the last couple of years. And this is probably the one downside of what we're doing in terms of the task-based approach, because the user's challenges have gone in the sense that the user just writes tasks, but at the same time the challenges in managing how we move tasks come back in the shape of having to write something like this, which is almost like a small operating system in many ways. And it's a great credit to John and Damodar that they were able to sort of make this work across these different architectures and to make it work efficiently too. So the idea with performance portability is that we want to be able to solve problems on all these different architectures, and so the fact that we have different machines and each company seems determined to lock us into their own little ecosystem is a bit of a challenge. And so we want to be able to rise above that in some way, and the way that we've chosen to do that is using COCOS, although we could use Raja or Oka, and it's possible that some aspects of SYCL and HIP also help us with this. And the idea really is that we have simple loops like the COCOS and Raja loops shown here, in that we have sort of a simple parallel 4, and they're very similar in some ways, and I think that those two efforts have been gradually brought closer together by the Department of Energy, and the overall goal is to have less duplication with a sort of smaller learning curve by writing simple loops once that can be mapped onto the different architectures. And with COCOS, COCOS has started off with Sandia Lab. It's a C++ library, and it provides backends to CUDA and OpenMP and HIP and SYCL. It's evolving very quickly still, and a lot more features being added to it continuously. It's becoming quite a very powerful sort of software library, and the idea is that it will eventually be an add-on to the C++ standard, and so there's a measure of kind of safety in using it in the fact that it will be part of the standard at some point, and Sandia is working quite hard to make sure that that happens. The abstractions that you have sort of control where kernels are executed, where data is allocated, and also how you map data to memory. And as we said before, the idea is to allow you to just write once and for that to be executed on all the different machines. And essentially that's done through some very clever C++, using lambdas and so on to enable the code to be executed using these anonymous function pointers. The challenge with using it, though, in the legacy code is that you want to make sure that you've got a way of still keeping your legacy code that hasn't been moved across. So John Holman put together this sort of layer that we have, which allows us to use our legacy codes, COCOS with different options, or even future interfaces should we choose to use them. So we've got this sort of thing that sits above COCOS, which is the kind of Uintah loop structure, and allows us to map onto our existing code, COCOS code, or anything else that we choose to put in the future. And we know that this has also been adopted by Amrex and HPX in a similar sort of way, maybe a little bit after we moved in that direction, but I guess independently. And the key features in this are that we've got our own sort of generic loop structure, and that we essentially have tools for things like locks. We have tags to manage where tasks are executed. Some things are sort of, the user can say, well, this is a CPU task, or this is definitely a GPU task, or they don't care. And so we allow for things like that. And we have the same kind of philosophy as COCOS, but it are slightly different. The Uintah loop structure sits above COCOS and maps down onto it. If you look at a stencil, what happens inside a stencil is that it's pretty straightforward for a time-stepping code. What we have is a data warehouse, an old data warehouse. We move information across in terms of the solution. So the task picks up the uold plus the halos in green. Remember the blue blocks and the halos. And then we do an incremental time step calculation. So we create new U in the stencil task here, and that involves this COCOS Uintah task using the sort of C++ 11 features for the lambdas, for the anonymous function pointers, And then we, essentially at the end of the step, we put the new solution back into the data warehouse and go round again. Memory is sort of controlled by COCOS views, so there's this sort of COCOS form of memory, and we use this COCOS abstraction layer to sort of map loops and to use architecture-aware loops, sort of memory structures and so on. The challenge with doing a lot of this is that we have users. Okay, so we have lots of users in sort of engineering. And let me be blunt, our users love writing C++. And let me even be more blunt, that's a problem. Because they love to write things that are really clever in C++. And they have lots of scope to do that. So we started to look at the performance of our loops, and I said to John, look, take the worst loop. And this loop had 800 lines. It did things like declare variables inside loops. It had all kinds of crazy stuff in there. So he started looking at this loop and sort of putting it into COCOS with the OpenMP backend. And he sort of improved the performance by a factor of 2.5 by just taking out a lot of this stuff, the clever stuff that our users had put into it. And then he started to look at the performance in terms of using more threads and cores, and you can see on this sort of table here that the speed went up by a factor of over 16 when we went to 8 cores and 2 threads when he'd introduced these loops. But to put it bluntly, legacy or clever C++ is more of a performance. Sorry, there's a typo there. Is more of a performance problem than Fortran ever was. With Fortran, all you got was spaghetti code. Now you've got code that's impossible to debug with some of the things that people do, and we've seen this, and it's a problem. And I know it's a problem at the labs too. So don't be clever. Is the message here. Okay, so with Hyper, what we also had to do was to essentially improve its performance because OpenMP didn't work too well. So Damodar basically decided to mimic MPI in some ways to get around the synchronization of OpenMP. And what he was able to do in a series of papers, some written with a group at UC Irvine to improve the performance of Hyper and to sort of get an order of magnitude improvement. Basically, when we started off with Hyper and OpenMP, we got a 3 to 8 factor slowdown because of excessive synchronization and short loops. And we were able to get around this and improve its performance by an order of magnitude. But I'll explain where we can get that information. And there are more details on this work in Ulrike Meyer's talk this afternoon if you're interested in this. Okay, so the boiler benchmark that we're using, essentially, we had this turbulent flow. So we had the turbulent flow part and we had the radiation part. And those are the two key pieces in terms of what we're trying to do. Now, the results I'm going to show you are very preliminary in some sense because we only had 2 runs of the whole suite on both the Summit machine and on the Frontera machine. So we didn't have a lot of chance to tune these results. So these are results that just came from the very first runs that we did. There's some details about the loops there. We have a standard sort of ray tracing radiation benchmark, and we have a standard turbulent plume benchmark, and those are the 2 things I'm going to show you. Now, these graphs are kind of hard to read, and I'm going to summarize them all in a hopefully a very neat way. But what they show you for the ray tracing is that the ray tracing ran out to 24,000 GPUs. It didn't scale so well at the very end because of some issues. And the turbulent plume scaled better, actually, out to 24,000 GPUs on Summit, and not quite as well on Frontera for reasons which I'll also explain in just a minute. But essentially, we got good scaling and good use. And given the fact that this was the first real run that we had, because the first run failed due to some sort of elementary errors that we made in terms of setting up the jobs, and so this was the first run that we ever did. So it's not as though this is a result of lots and lots of runs and trials, because we just didn't have access to the machines that much. So what I'm going to show you is the relative node performance, because what we need to do is to normalize CPUs against GPUs. And so we're looking at how long each element takes to execute each element per node takes to execute. So we're looking at the execution time over the elements per node to try and get some relative picture of performance. And we're going to look at the relative slowdown that we get over using the Frontera machine, which is the Intel CPUs, against the Summit machine, which is the V100's GPUs. So here we go. So what we've got here is that the sort of purple line at the top is the Summit scaled, communications performance, the peak data transfer rate. We'd expect to see about a factor of 12 improvement. If you look at the raw CPU rate, we'd expect to see a factor of about 10. And what we've got here are the blue line represents the relative slowdown. And the three sets of cases. On the left-hand side, we have the small cases, where we get closer to seeing the sort of CPU performance. The medium cases, where we've got a speed up which is close, a slowdown which is closer to what we expect from the relative data bus speeds. And on the right-hand side, for the very large cases, we hit an issue with radiation on Summit. So Frontera did actually pretty well against Summit in this case, because Summit was having difficulties caused by the sort of global reductions that we were doing in the radiation, where we had to bring all the information together to reflect the global connectivity. And so what's interesting is we see this factor of about 10 to 12 improvement in performance. And it was interesting, I got sent a copy of one of the computing reports from Lawrence Livermore that said that their Marble code saw the same thing over the CPU, when you compare CPU performance over Lassen. And I've also just recently, last week or so, saw something on a different architecture where somebody else had seen the same thing for a very different application. So for lots of these codes where you get this single flop per word, these data bus improvements are the things that really count. For the helium plume, things really didn't work out very well on Frontera because we had some poor run configurations, so Frontera was a lot slower than Summit, something between 40 and 100 times slower, and but that was because there was a problem in terms of how the Frontera runs were done. As I explained before, we only had chance for 1 or 2 runs before our time ran out. So the results that we have show that we were able to run our benchmarks out to the full range of Summit. We were able to push the sort of asynchronous approach, plus this portability approach, out to 24,000 GPUs. The scaling was pretty good for a very first attempt. It broke down on Summit a little bit because we only had sort of 64 cube patch per GPU, and the reduction communication cost dominated, which is why on 24,000 GPUs it kicked back up again. How much memory is available on GPUs is an issue, and Frontera really had a surprisingly slow bandwidth compared to Summit, which was interesting because I wouldn't have thought that was the case, in terms of the architectures. I didn't look at them too closely, and so Summit came out really well in this sense, in a way that was unexpected to me. So what we've got here is a good porting strategy for exascale. The use of something like CoCos really helps, and I've seen a number of other efforts in this conference where people have been using CoCos with success. And what we're trying to do is to push these ideas out further onto Aurora and Frontier when we can. So data movement architecture is really key. Flops are less important for these applications, and the GPUs really proved to be much better at this than I thought. There are a bunch of references. You can go to the SKI webpage, and if you search on any of the authors' names, you'll find a whole bunch of papers. But what I want to do is just finish with a final thought from Snow White, which is mirror, mirror on the wall, who has the fastest data bus of all? That's the key thing. And if we compare the different sort of architectures, certainly the CPU truck is good. I mean, it's fast. You can get all your data in. But arguably, it may be worth going to the store in your sports car because it just does go kind of faster when you can. And there I would like to stop.
Okay, thank you. So we're just about at the time, but we'll take about 5 minutes for questions since we have a long break after this. And the first question here.
Thanks a lot. I found your presentation very enlightening because it seems to me that the sort of phase space of computational phase space that you guys are in is very similar to what sort of phase space we are in high energy physics. And my questions are sort of around this, that we are facing the same sort of task scheduling problem that you described. But do I understand correctly that you guys just use a very custom task scheduling system?
Yes, it's entirely our own. Yeah, everything's ours. Yes.
And did you ever consider trying some standard task scheduling, let's say HPX, which we are considering?
Yeah, sure. I mean, but you know, they're essentially competitive hours. I mean, we've been working with tasks. I mean, the original code came from Steve Parker in the late 1990s, and you know, we've been working with asynchronous. I mean, I pushed to make the tasking asynchronous in about 2005. So we've been working with asynchronous tasking for 20 years nearly. And so, you know, I mean, sure, we could change over and use one of these other approaches, but, you know, arguably we've been sort of trying to show what's possible with this as a kind of, you know, as a research example. And yeah, other people doing the same things with different, with the same sort of successes as well. So yeah, this is not the only approach for sure.
In the end, my question was mainly that how could we potentially steal your task schedule?
Hey, you can just go to GitHub. It's all open source. And, you know, I mean, and it's not, I mean, and we would work with anybody who wanted to work with us in terms of understanding it. You know, it actually, the tasking is, you know, people have very complicated structures, but actually the algorithm is really simple. I mean, what you do is you prioritize execution of anything that does external communication. And then otherwise just maybe try and keep things going that have the most external connections from that task. But prioritizing anything that does external communication, is key, because external communication is the slowest thing in your system. And you know, you can do so many more flops over the cost of one communication. So the tasking itself, the core algorithm is not difficult, and we've known that for about a decade. It's just understanding what to prioritize and how you prioritize what you do.
Thanks a lot.
Other questions?
So I have one question. You raised the issue of debuggability of C++ code. You can kind of gonna bounce the ball. How easy is it to actually develop a task-based program, and especially when it comes to debugging, when you see, you know, something falls in a task somewhere?
Oh yeah, okay, yeah. Well, you know, debugging at scale is really difficult anyway, and so, you know, I've had some amazingly skilled people working with me, and so they get really excited. They say, okay, this problem that crashed on 500,000 cores, I managed to get it to repeat on 30,000 cores. Now we can debug it. Okay, and so that's the kind of thing that we do. And, you know, standard tools, except we did crash one of the DOE systems when we tried to use the debugger on the whole machine, and they weren't very pleased with us. They told us off for that, not surprisingly. But yeah, I mean, the standard debuggers do work, and, you know, you're right in that debugging the task-based stuff is potentially problematic. And what we do is we instrument everything. So if you instrument everything, you can track how much time is spent in communications and how much time is spent waiting. So performance often comes down to the fact that all of a sudden you seem to be spending more time waiting and there's not much to do, and that's when scalability drops off. But yes, seg faults at scale are a real issue, and you know what the trick is to really reproduce them at smaller scale, and then you can use a debugger, and we've done that on the different machines. I mean, it isn't. I think you know, it's not the user's job to debug that, because often those are not user issues, those are runtime system issues. And that's where the difference is, because the user's responsibility is to just write the tasks. And it's the sort of the runtime system team's job to write the runtime system that makes those tasks execute well.
Another question?
thanks for this really nice presentation.
Thank
I
you.
had one more question about the tasks. So I'm curious about the granularity of the tasks. So can you...
Oh yeah, I
from
mean,
the
well, that's the main difference between CPUs and GPUs. You've really got to crank up the patch size. So the patch size, typically, when we're running on CPUs, you can run patches that are sort of 16 cubed, 32 cubed, 64 cubed, but now we're talking about, 1024 cubed or something, big patches. You have to have big patches on GPUs. So you just keep, and that's one of the differences in, but then, you get used to changing the patch size on the different architectures that you're running on, and that's just knowledge that's accumulated as you go through the process. Yeah, because you can't, you have to hide the overheads as well. It's really important to hide the overheads, so there has to be a lot of work in those tasks. And in fact, that goes back to, some of the tasks that our engineering users put together were pretty small. And so we had to merge a lot of these tasks. And they even put something together to merge some of these tasks, because sometimes what might be a natural task from an engineering point of view is too small to be a good task in terms of execution. It doesn't have enough flops inside it.
So if I may follow up and ask, so actually this task size is really something that you have to tune. It's not something that somehow automatically is determined by your system.
You could do. I mean, it would be easy to build a way of doing the runs to determine what the task size should be. But we haven't done that because, you accumulate that knowledge pretty quickly, and it's not hard to see. And you could, you could even, if you just got one GPU, you could run our code runs on everything from laptops through to Summit. So you can run it on your laptop with your one GPU, and you can determine what the right patch size should be in terms of the information that you get back about that if you want to do that. But yeah, I mean, we found very early on there has to be enough work inside the task.
Okay, well, I think I should cut it off there, but thanks for a very interesting talk, and hopefully those who have additional questions could talk to the speaker one-on-one during the break.